Today's topic concerns the motion of charged particles in uniform electric fields. And this is going to be a section that will refer you back to your good old kinematics and dynamics and energy expressions from your first physics class. The same rules apply. So we can talk about, again, in magnitudes, the force of due to an electric charge is just, on an electric charge, is just that charge times an electric field that it experiences. Newton's second law still applies, so F equals ma. If I set the two equal to each other, I can say that the acceleration that results from an electric field is just the sign of the charge, the value of the charge, times the field divided by the mass of that charge. So if E is uniform, the acceleration is going to be a constant of the motion. If the charges are positive, the acceleration in the electric field will be in the same direction. If they're negative, they'll be in opposite directions. And the same rules of kinematics apply. So for example, the old expression x equals 1/2 at squared for particles starting from rest, subject to a constant acceleration, can now be written as 1/2 times QE over m times t squared. Velocity, we used to write as the product of acceleration times time. I can write that as q times e over m times t. Velocity squared, I can write as 2qe over m times x. I can write my kinetic energy, 1/2 mv squared. Now it looks like qex. And this stands to reason. Remember, the electrostatic force is a conservative force, so I can write kinetic energy, or work in this case, as a force, the electrostatic force, through a displacement x. So it all follows the same logic. It's very, very nice. Let's look at a simple example of a parallel plate capacitor. So suppose I have the following situation. Suppose I have a positively charged plate on the bottom and a negatively charged plate on top. And suppose, so this is going to give me an electric field that goes uniformly from the positive plate to the negative plate, like so. Suppose I send an electron through this field. Well, an electron has a negative charge, so if I have an electron, it's going to come into this field, and of course its motion is going to go like this. It's going to be attracted to the positive plate, and it will undergo what we would call, back in our old kinematics days, projectile motion. So this being the case, let's say this is the x direction, E is going to be in the positive y direction, right? E is going in the positive y direction. The electron is going to be pushed to the negative y direction. And we can write then, suppose we want to calculate the electron given an electric field. Well, we can write the acceleration as minus E times the size of the electric field divided by m in the j direction, or in this case, negative y direction. The velocity of the electron, whatever it's given, is a constant in the x direction, but in the y direction, it's going to be equal to the acceleration times the time that it's in between the plates, or minus E times the electric field over m times the time. The displacement in the x direction I can write as v naught, whatever velocity it has, times t. The y displacement, it starts at 0 displacement, but it's going to continually sink downwards in the field. I can write as 1/2 at squared, which I can then write as minus e t squared over 2m. Moreover, since I can write t as x divided by v naught, I can write this as minus e x squared divided by 2m v naught. So I have all these expressions that can describe the motion of this electron. And of course, the path, no surprise, is going to be parabolic. Let's put some numbers in just for fun. Suppose I have a velocity, an initial velocity in the x direction for the electron 3 times 10 to the 6th meters per second. And let's suppose the electric field between the plates is 2,000 newtons per coulomb. Let's say that the length of the plates is 0.1 meter. Let's find the acceleration, the time it spends between the plates, and the y displacement of the electron after it's gone through the plates. So first off, I write the acceleration is E times E divided by m. That's 1.6 times 10 to the minus 19 coulombs. That's 2,000 newtons per coulomb. Mass of the electron is 9.1 times 10 to the minus 31 kilograms. Put those numbers in. I'm going to get that it's going to minus 3.51 times 10 to the 13th meters per second squared, of course in the negative j direction. The time that it spends between the plate is equal to the length divided by its velocity in the x direction. We said that the length of the plate is 0.1 meter. The velocity is 3 times 10 to the 6th meters per second. Therefore, the time it spends between the plates is 2.33 times 10 to the minus 8 seconds. If I want to know the y displacement of the electron, that's 1/2 at squared. Well, acceleration is 3.51 times 10 to the 13. Time is 2.33 times 10 to the minus 8. Put those numbers in. I will get a displacement of minus 1.95 centimeters in that time. So this is just a quick illustration of how we can use Newton's laws and again our expressions for energy from Physics 1 mechanics type problems to solve motion of charged particles in uniform electric fields. Next time, we'll talk about a special type of electrostatic calculations, a very, very, very useful method to calculate electric fields, and that's called Gauss's law. So we'll pick up with that next time.